Hello, honors physics students. Let's get started going over your homework. We'll look at the conceptual questions from the textbook, starting with number 4, which asks you to make an analogy about cars and traffic and circuits. And remember, we're really big on analogies, both in electrostatics and now also in circuits, trying to visualize the motion of all these tiny, tiny objects and related to things we're used to. So we've already introduced the plumbing analogy, and we had the example of the marble in the tube, and then we had the analogy with the students in the hallway, and now we're introducing the traffic analogy. Okay, so hopefully you were pretty good at figuring out what would go where, that the charge is moving could be represented by the cars, right? A whole bunch of little things moving throughout the wires, represented by, for maybe like, a traffic copter above watching all the patterns of the flow of traffic, all the cars moving, right? Okay, what about the current? Well, probably said that was something about the cars moving, right? Specifically, since we said current is the rate of charge flowing, which would be the rate of cars moving, but the word rate carries with it a lot of meaning that maybe you shouldn't ascribe to it, because the first time we ever introduced the sort of rate, you really meant speed, or later on we talked about velocity when it came direction, but remember, rate is really how anything changes with respect to time, and we want to make sure we're clear about this, that when the charges move, it's not about how fast they move, it's about how many of them move. And so I want to make sure we're very clear that even with this one, it's not how fast the individual cars are moving, but how many of them move in a given amount of time. Even if you are watching one point along the highway, if there's a lot of cars flowing past, even if they're moving slowly, that's still a large rate of cars moving. That's still a large flow, right? Certainly also if it's even just one car moving really fast, that's also a large flow. But when we are visualizing what's happening within the wires, we're talking about billions and billions of charges, and we'll soon talk about the fact that they don't move very fast. It's just that if a lot of them move, that's a large current, and even if they're moving slowly, it's still a large current, but if only a few of them are moving, that would be a small current. So it's a different way of thinking about rate. All right, number 5 is about correcting the statement about 10,000 volts of electricity surging through, right? Of course, that doesn't make any sense. Here we go back to our hiking analogy, really one of the first analogies that was most successful in explaining potential difference, right? And in our hiking analogy, what was voltage? Well, it was like a change in elevation, or really the height of the mountain, right? The mountain is there. It represents a change in elevation, so the voltage is there. So just like in our hiking analogy, the mountain doesn't go anywhere. It doesn't make any sense, right? The mountain doesn't move. Voltage doesn't move either. So we always want to make sure we're using our vocabulary very, very carefully, right? When we think about the circuit, what is it that moves? That's the charge. When charges move, that flow, that rate of charge moving, that's current. But the voltage is just there. The voltage is sort of like this electrical pressure causing the charges to move through the circuit. So if you are ever encountered someone saying something about voltage moving or voltage flowing, they're using their words incorrectly, and you should also be very careful how you're thinking about it and how you're using your words. Voltage doesn't go anywhere. And when you think about the mountain moving, that makes it seem rather silly. That's why the analogy is so powerful. It really helps us relate sort of an abstract thing, something we can't see, to something that we can see, something we can visualize. And that's why we always go back to these analogies. Okay, so let's go into our our notes. And if this were a regular class, I'd ask you to answer these two questions as I do now. So right now in your notes, I just want you to write down both the questions, leave a little bit of space in between 1 and 2, pause the video, and write down your thoughts, see if you can figure out the answers. Okay, so for number 1, this goes right back to what we had done last class, where we took some data from the simulation, and then you watched the video of an actual experiment being done, and of course we plotted a voltage versus current graph. Now it's so important, just like we've done all throughout the year, that you of course recognize that the title of the graph means something. The title of the graph tells you what's being plotted and what's where. The first thing is always on the vertical, the second is always on the horizontal. So specifically, this is voltage on the vertical, current on the horizontal. From the data we got, from the data that we saw in the video, we got a nice straight line, and we figured out, of course, that the slope is voltage over current, and by relating that back to the numbers involved, we realized that is equal to resistance. And so that's just, going on with all of our graphical analysis throughout the whole year, that the slope of a graph usually has some meaning. And so this here is resistance for the slope, the ratio of voltage to current. All right, for number 2, if you got a little bit stuck, I'll give you a little bit of a hint, and then maybe you can pause the video and try again. It helps if you think about the original equations, right? You're going to be multiplying current times voltage. Think back to the first time you're introduced to either current or voltage and the equations that went along with them. And then see by manipulating them together, by multiplying them, if you can figure out what it represents. See if you can do that. Okay, so just the other day, the first time we'd seen current, it was given as the rate of charge passing, right? So delta Q over delta T. That's the first time we saw current, not when we saw it again in Ohm's law. So hopefully you're starting with this. For voltage, well, remember, the old name for voltage was potential difference. So even on this topic, in our previous topic, when we first introduced to potential difference, That was the change of potential energy over charge, right? Energy per charge, or it was work per charge, but I want to do it as energy per charge. So hopefully now that you see it written side by side, you see the charges will cancel. Yes, I know there's a capital Q here for an accumulation charge, there's Q here, but the point is that doesn't really matter. It's still charge canceling, so left with a change in energy over time. I leave it as more generic energy here because it doesn't actually have to be change in potential energy. Now we want to think about it as change in any sort of energy over time, and you should recognize this. Change in energy over time, or work over time, that of course is power, right? So power, this is more like a mechanical power, this is like electrical power, current times voltage. We can also see this from the perspective of the units involved. If we have current times voltage, let's think about the units. Right? Current is measured, we know, in amps, and voltage, well, that's measured in volts. That's a nice easy one. So this would be amps times volts, or amp volts. And so the unit of electrical power is the amp volt. I'll tell you right now, no one uses the amp volts. So let's manipulate this also in terms of the units, how these are defined. So let's think, what is the amp defined as? Well, you can see it right here from the equation in case you forgot it. Look back in your notes from last class. It's charge per time, so that's of course going to be coulombs per second. What about the definition of the volts? How was that defined in terms of other units? Well, if you don't quite remember, again, the equation is right here. So it's energy per charge. That's going to be joules per coulomb. And here we see, of course, that the coulombs cancel. We're left with joules per second. And hopefully remember, what's a joule per second? What? What? Oh, what's that? One more time. What's that? Oh, yes, it's still funny, right? I told you months ago that's going to be funny. It's still funny, right? No matter what, it's a horrible physics joke. Look, there's only like 5 decent physics jokes, and this is one of the better ones. The other ones are even worse than this, right? So we have to take them as we can get them. Yes, so it's the watts, right? 1 watt is 1 joule per second. That's power when it's mechanical power or electrical power, and this should make sense, right? Let's say the light bulb goes out, you go to the hardware store, or maybe you go online now these days to order a new light bulb, and you have a whole assortment of light bulbs. You have the 40-watt light bulb, the 75-watt light bulb, the 100 watts light bulb, right? So what's the advantage to using a 100-watt light bulb versus a 40-watt light bulb? Well, it's brighter, right? It gives off more energy per time. So 100 watts is 100 joules per second. In fact, sometimes the power of a light bulb is called its wattage because it's measured in watts. Going along with that, right, voltage is potential difference. It's measured in volts. It's called the voltage. And then some engineers actually call current amperage because it's measured in amps. So wattage, amperage, voltage, right? They're just sort of colloquial names for these sort of things. Since most of the times in circuits, the resistors we use often, I shouldn't say most times, but a lot of times they're light bulbs, we just want to make sure we understand that for light bulbs, the power then translates to the brightness. This comes into play a lot of times when we compare one resistor to another, one light bulb to another. We want to know how much energy per time it's giving off. What's the usefulness of that resistor in this case? How bright is the light bulb? Okay, so now we have our new equation that power equals current times voltage, but I'm going to give you a chance to rearrange some things here and try to derive 2 other equations. So we take the definition of resistance, which we remember, right, it was almost all as delta V equals IR, and I want you to just play some algebra games here. Work your algebra magic and work this equation into the power equation in 2 different ways, both to get resistance in there to relate it to power. In one time you replace the current, the other time you replace the voltage. So pause the video, try it on your own. It's not difficult stuff. I'm sure you'll be able to get it. Okay, so here are the 2 equations you should have derived. If you replace the current, you should be getting delta V squared over R. If you replace the voltage, you should be getting I squared R. Not really difficult stuff here. We're going to box all 3 of these in as new equations. They're really all the same thing for electrical power, but just, provide a little shortcut depending on which term is given, rather than always starting with I delta V and then having to use Ohm's law to replace things. The more useful way to use this, though, is oftentimes we'll be dealing with different arrangements of resistors, specifically maybe light bulbs, in circuits. And you maybe ask questions about which is the brighter light bulb, which resistor is giving up more power. And so the way we really use these equations is when we compare those resistors. And when doing so, because all different terms to use and can be kind of confusing and get lost in the algebra, you want to choose one of these 3 equations that has some value that is the same between those resistors. Right now, it's not going to make a whole lot of sense, but pretty soon when we start dealing with different arrangements of resistors, in certain arrangements, maybe the voltage is going to be the same, in which case you pick an equation with voltage, and then you just see how the other things change around it. Or maybe in a different arrangement, maybe the current is going to be the same. So you pick one of these equations that has current in it. This way, it sort of eliminates one of the variables. It just keeps that constant, and you can see how the other two variables change around it. Otherwise, as I mentioned, you can really get lost in the algebra and lost in the logic, trying to figure out which is the more powerful resistor or which one gives off more light if it's a light bulb. And so this is a nice little shortcut for figuring out which equation to use.